Alright, hey AP Chemistry, here is a video answer key for the Checking for Understanding on Acids and Bases Part B. So let's look at our first question. So it says, a saturated solution of hydrobromic acid, HBr, a strong acid, has a pH of 3.9. Just by looking off the back, this is a low pH. It's acidic. Identify whether the solution is acidic, basic, or neutral. Acidic, pH is less than 7. All right, then we can look at the rest of this from an eye of a strong acid. What is the concentration of H+? Well, since I already know that the pH is 3.9, 10 raised to the negative pH is equal to the concentration of H+. The pH is equal to the negative log of H+. If I want to do the inverse of that, if I want to solve for H+, I have to raise both sides to 10. That's how you solve for the inverse of log, is raising with a base 10. So 10 to the negative pH is equal to H+. Therefore, 10 raised to the negative 3.9 is equal to the concentration of H+, which equals, and then keep in mind, for if we were asked about significant figures, since I have two significant figures in my pH, and I have one decimal place, since I have two sig figs here with one decimal place, that means my answer must have had one significant figure. I need one decimal place. The number of decimal places is how many sig figs came in my answer. So one decimal place means my answer must have had one sig fig. The number of sig figs is how many decimal places you use in your pH answer. So that comes from our notes if you want to check that. So 10 raised to the negative 3.9 is equal to 1.25 times 10 to the minus fourth. Actually, let's say 1.26 times 10 to the minus fourth molar. And then if I want to use the correct number of significant figures, since there's one decimal place, I must have had one sig fig. So 1 times 10 to the minus fourth molar. What is the pOH? Well, it says it right up here. 14 is equal to pH plus pOH. That's given to us. So 14 minus pH is going to be equal to pOH. Therefore, 14 minus 3.9 is equal to 10.1. That's my pOH. Then, since I have my pOH now, it says, what is the concentration of OH minus? 10 raised to the negative pOH is equal to the concentration of OH minus. And remember, if I have a solution, I'm going to have some amount of H plus and some amount of OH minus. If it's acidic, I have more H plus than OH minus. If it's basic, I have more OH minus than H plus. So let's see, if it's acidic, this number should be a lot larger than this one. So let's see, 10 raised to the negative 10.1, yeah, it's going to be a very small number. 10 raised to the negative 10.1, I get 7.94 times 10 to the minus 11th. 1 sig fig is 8 times 10 to the minus 11th molar. And yes, this is a lot smaller than this. My concentration of H plus is a lot greater than the concentration of OH minus, which further verifies that this is an acidic solution. All right, let's look at the next question. That is a weak acid. Now, this is not a strong acid, this is a weak acid, so I'm going to need to do more stuff here. So, hydrocyanic acid, HCN, is a considerably weak acid with a Ka of 4.0 times 10 to the minus 10th. Write the dissociation equation for hydrocyanic acid and water. HCN aqueous. It's a weak acid, so I need an equilibrium arrow because it's going to go back and forth. And I get H plus aqueous plus Cn minus aqueous. Another way of writing this all full out would be something like HCN aqueous plus H2O liquid in equilibrium with H3O plus aqueous plus Cn minus aqueous. That is also the same expression, just mine is a little bit more simplified. I'm going to work with the more simplified one. Write the Ka expression. Well, Ka is the equilibrium constant for the dissociation of this acid, so products over reactants. Concentration of H plus, concentration of Cn minus, all over concentration of HCN. And then finally, it says calculate the pH of a 2 molar solution of hydrocyanic acid. Well, since this is a weak acid, I'm going to need to use an ice table because I don't know how much H plus is going to dissociate unless I use the equilibrium dissociation for the acid. So I'm going to rewrite the dissociation expression, HCN, H plus Cn minus, and set myself up an ice table. Give me myself my ICE. ICE. And now, once I solve for my equilibrium concentrations, if I get my value of x, which is going to be my value of my products at equilibrium, that's going to be my value of H plus at equilibrium. And once I know my H plus, I could solve for my pH by using the negative log of my H plus. So let's get there. So I have 2 molar initially. And initially, nothing dissociates. Then over time, I get a bit of dissociation. So let's say minus x. And that minus x is the same amount that's going to be added to H plus and Cn minus. So how much broke off HCN is how much the H plus and Cn minus were made. And then combining them, 2.0 minus x, x. And then I could set myself up for writing an equilibrium expression. I already did that in letter B. So H plus times Cn minus over HCN, x times x over 2 minus x. So x times x over 2 minus x equals the Ka, and we already know the value of the Ka. It's 4.0 times 10 to the minus 10th. Now, since this is a very, very, very small number, we can assume that this x is going to be very small, almost close to 0. So it's going to say x is approximately equal to 0 because Ka is a lot smaller than 1. And this simplifies my math. Now I have x squared over 2 is equal to 4.0 times 10 to the minus 10th. Right? X times x is x squared. I got rid of the minus x, it just became 0, so 2 equals this. Now, if I want to solve for x, I have to do 2 times 4.0 times 10 to the minus 10th, which is just going to be 8 times 10 to the minus 10th, but I'm just going to plug it into the calculator. So I want to solve for x, so I'm going to do 2 times 4.0. I want to isolate that x times 4.0 times 10 raised to the minus 10th, 8 times 10 to the minus 10th. And so I'll have x squared equals 8 times 10 to the minus 10th. If I want to solve for x, I take the square root of both sides. Second square root, second answer. I get x equals 2.83 times 10 to the minus 5th molar. Because x is going to be a concentration at equilibrium. If I want to use the correct sig figs, I should have like 2.8 times 10 to the minus 5th equals x. And now, this value of x is equal to my concentration of Cn minus at equilibrium, and it's equal to my H plus at equilibrium. So x is equal to my concentration of the concentration of H plus at equilibrium, and that equals, like we said, 2.8 times 10 to the minus 5th molar. Now, if I want pH, I just got to take the negative log of that. pH is equal to the negative log the concentration of H plus at equilibrium. I added in the at equilibrium because that's going to be for weak acids, but this is in general how I get the pH. I take the negative log of H plus. If I do the negative log of 2.8 times 10 to the minus 5th, I get our answer, negative log of 2.8 times 10 raised to the minus 5th. I get 4.55. Now, this I made 2 sig figs, so I'll have 2 decimal places. 4.55. So my pH is equal to 4.55. All right. Then number 3, I have a strong acid and dissociates when placed in water. A strong acid 100% fully dissociates. So if I have 10 of the acid particles, let's say this is H plus, and this is going to be NO3 minus, this is going to fully dissociate completely. So I'm going to have HNO3 aqueous, and it's going to be a full arrow, not a double arrow. H plus aqueous plus NO3 minus aqueous. 100%. So that means if I have 10 of these and it fully dissociates, I should have 10 of the H pluses and 10 NO3 minuses. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. 100% fully dissociates means they break apart completely. And then finally, I get to the last one. Identify the conjugate acid-base pairs in the following acid-base reaction. All right. Remember, an acid takes the form HA. A base, or something with a plus sign, and the base takes the form A minus or OH minus. So I have to find those, and that could help me figure out the other ones. So I have ClO minus, that's definitely a base, has a minus charge. HCN, HA, this is definitely an acid. And then if these two react and interact, this base is going to take an H plus from this acid. And so on this side, now I have CN minus, which becomes the conjugate base. I removed a proton. And now on this side, oops, this is a typo. That should not be ClO minus. I have ClO minus and I have HClO. This is my conjugate acid, and that comes from my base, and it gained an H plus. And so now I could identify these acid-base conjugate pairs. My acid will be HCN aqueous, and its conjugate base will be CN minus aqueous. My base will be ClO minus aqueous, and my conjugate acid will be HClO aqueous. With that typo, if you put HClO minus, I won't mark you down, but that should just be HClO aqueous, not a minus charge. All right. For the helpful challenge, I will post separate videos, but these are the video answer keys for versions A and B. They will separately be found on my YouTube channel, in the Google Classroom, and in the Remind.